Hello, welcome to Picture Me Coding with Erik Aker and Mike Mull. Hello, Mike, my friend.
Hey there.
Hope you're doing well.
Doing all right. We now have a Picture Me Coding account on Blue Sky.
Oh yeah.
If you're not on Blue Sky, I recommend it. It's kind of like nice Twitter at this point in time.
We also have an email address. You could send us email, podcast@picturemecoding.com. So you can reach us at Blue Sky. You can reach us by email. And we actually started a threadless shop, not because we expect to make a huge amount of money out of it, but because we thought that if you wanted to show off your awareness of highly niche music podcasts about software, you could get a shirt or a coffee mug or a sticker and proudly say, I am a Picture Me Coding listener. And everybody you know will be like, what's that?
I thought it was all about making money. I guess
I don't think we're going to make any money off of it. That was not my intention. My intention was, hey, let's give our audience a way to show their appreciation of the show by drinking out of coffee mugs.
I've been debating whether or not it is morally acceptable to put Picture Me Coding stickers on the backs of signs like people do with their band stickers and zine stickers and stuff.
I don't know. If you own the sign, it is, right?
Yeah. The old man in me sees that and thinks, damn you kids for putting those stickers on that sign. But
there's
also,
20% of you that's still kind of punk rock in there, I can tell.
Yeah. But there's 20% of me that thinks, hey, that's kind of a cool sticker. I'm going to check out that band. So,
Mike, this week I've been listening to minimalism, and it's a category of music that I cannot claim to know much about, but I know the name Steve Reich. I know the name Philip Glass. And somehow earlier this week, I just felt like there was too much going on in my brain. And I wanted something like a frequency to tune into, to be able to ignore everything external to me and also these other, like these noises in my head. And so I turned to this record by a group. Now I just found them on Spotify through looking up Philip Glass stuff, and they're called Third Coast Percussion. They're from Chicago. They're these people who are like music academics, like classically trained musicians. They have PhDs, and they're percussionists, but they play marimbas and other percussion instruments. And they make these records that you could kind of vaguely think of them as like soundtrack-ish, but they're so layered and complex, you have to lean in to listen to them. That's what Steve Reich said about them. Anyway, they had this record that I loved, which is called Paddle to the Sea. So I started with that, and then I got pushed on to a more recent one called Perpetuum with Philip Glass. And they also have one this year called Currents Volume 3. I think everyone should check out Third Coast Percussion as soon as possible. If you're like me, you're confused about the world and you need something to wash over you and tickle your brainwaves, this music will get that job done. So go out and listen to them as soon as possible. I think you in particular, Mike, should listen to Third Coast Percussion.
should I do it right now? Should we suspend the podcast for a while? And I'll go
maybe.
listen.
Yeah, maybe. We'll just cut out. Go listen to them and we'll cut out the silence and skip straight ahead to the future.
Okay. I like Philip Glass and Stephen Reich, although I have to admit it's a little bit of a mood thing for me. Sometimes I'll listen to them and I'm like, this is amazing. I really like this. It has a sort of resonance in my brain. And there are other times where I listen to it and I'm like, oh my God, this is so repetitive. Please make it stop. So not sure exactly why, what sort of mood I need to be in to make it satisfying, but it does seem to vary for me.
There's something about the music that's analogous to lasers. You know how lasers are those frequencies of light that are all in synchrony, right? That's what's going on. This is lasers music.
That's an interesting thought.
And you blast your brain cells with it, and then your brain cells go in that same laser synchrony. Your brain cells emit those photons and bounce around in the middle inside your head.
I used to work for a guy who did work with lasers, and one of the things that he would do is he would take one type of laser and use it to power another type of laser. So you can sort of think of this music as being a laser that turns your brain into another type of laser.
Yeah, I mean, if you're listening to us, doesn't that sound like the coolest thing in the world?
Sounds pretty cool to me.
What have you been listening to, Mike?
The album I've been coming back to a lot recently is by a band called Porridge Radio, and I don't know where the name comes from. The album is called Clouds in the Sky, They Will Always Be There For Me. This is a UK band from Brighton, basically indie rock. It's musically pretty normal, but I like the lyrics a lot. I keep listening to her songs, and every once in a while I'll be like, hey, that really sounds like my life. I get that. It's by turns a little bit melancholy, but there's an interesting track on the very last track on this album is called Sick of the Blues, which is kind of literally about, I'm kind of over being sad. I'm just going to be happy now. So it's kind of a nice track.
Oh, we should blast them with our Third Coast percussion laser from over here in California. We fire it at them over there in the UK.
Yeah.
See if they get on the right frequency.
Probably cheer them up.
Mike, you know me. You know that the thing my heart ardently desires above all other things is to have written a correct program. I care if it's fast, but only if it's correct. I care if it's readable, but only if it's correct. I like those other things, but I want it to be correct first. If I get a ticket at work and the ticket says, when the bank account holder transfers negative dollars to somebody else, I want our program to drain their account entirely. We own their money now. Then that ticket might be wrong, but damn it, I want to correctly implement what the ticket says.
That sounds like a noble goal.
It's noble is the word for it, yes. So actually, no, I've been thinking a lot about formal verification lately, and so I wanted to talk to you on the show today about formal verification. I find it's like always confusing when I hear about formal verification tools because in the ether and in the news, there's like murmurings and there's all these different tools, and I've heard about loads of them over the years. But here's the thing: I've virtually never met anyone in our field in software engineering who actually uses these things. Now, that may be because of, the environments I'm working in. I guess that's not quite true. I used to work with chip designers, and they had like a formal verification tool for their chip designs for microchips. Anyway, this is actually inspired by two things. First, I've been reading this pretty funny book. It's fascinating, and it's actually by Leslie Lamport. There's no print copy of it, but you can get it for free online. It's called A Science of Concurrent Programs. And it builds up in this rigorous way the origin of TLA plus. Like, here's what TLA plus is founded on. This is the science underneath TLA plus. But then I also was reading this week, there's a description of something called automated reasoning that appears on Amazon's science page. So Amazon Science is an organization within Amazon that focuses on research. And I was like, what's automated reasoning? That sounds interesting. And so here's how they describe automated reasoning. Automated reasoning is a specific discipline of artificial intelligence that applies logical deduction to computer systems. Automated reasoning differs from other AI technologies, such as natural language processing, which focuses on training computers to understand written or verbal speeches. Instead, automated reasoning uses logical models and proofs to reason about the possible behaviors of a system or program, including states it can and will never reach. And I thought, well, that sounds promising.
It does. I'm sure it's simple too.
Simple to implement, simple to use. I want to feed my punch cards into the automated reasoning machine and have it tell me, yeah, this is great. You did a good job. You've successfully implemented the ticket. Is that future coming, I wonder?
I think so, probably for some version of punch cards and some version of machine.
That's a very hedgy answer. So on the Amazon Science page, they have a paper listed here called Model Checking Distributed Protocols in Must. And I've heard of other systems for like checking or verifying distributed algorithms, distributed programs. I was curious about this, so I just skimmed the paper. And I found this chunk of introduction, which I want to read to you. Here's what they say in the introduction of their paper about their tool called Must at Amazon. Despite significant research advances in the past years, formal methods are yet to be integrated in the development process of distributed systems. A major hindrance in their adoption is that existing techniques fail to adequately balance the conflicting desiderata of researchers and programmers. Researchers typically design powerful, yet expensive, reasoning techniques for programs written in domain specific languages, while programmers prefer mainstream programming languages and do not tolerate non scalable tools that interfere with their development. As such, while domain specific languages for distributed systems offer abstract modeling and systematic exploration for finite state abstractions, they do not integrate well with the rest of the software engineering process. On the other hand, tools for systematic concurrency testing built on mainstream languages do not provide adequate interfaces for abstract modeling. For example, no support for data non-determinism, multiple communication primitives, etc., and or do not provide any verification guarantees. Did that make sense to you? What I just read?
Parts of it. I was looking through it as well, and there some of the things that they complain about the tools not providing are things that I quite honestly did not understand. That second thing, especially. So they say something about data non-determinism, and then
Yeah.
some other property.
Multiple communication primitives.
Yeah, communication primitives. And I'm like, okay, I don't know what that is, but I'll accept that the tools do not do it well. I think maybe they're talking about things like TCP and UDP, but I don't know.
So I read this introduction and kind of chuckled to myself because I was like, isn't this the same thing everybody always says about formal verification for people like us? The researchers are building these tools, day-to-day developers like us are generally not using them. So I wanted to talk more about formal verification in this way. Who's using it? What is it? Am I ever going to use it? It's kind of like, you ever go to one of those neighborhoods where they have like a real estate storefront and they paste in the window these like papers, or maybe there's even a TV screen, and it'll be like, here's this lovely property with 8 bedrooms and it's only $24 million. And you're looking in the window and you're imagining like, wow, what would it be like to live there? That looks great. That's me. I'm at the formal verification storefront. I'm looking in the window at the properties that the formal verification storefront is offering for sale. And I'm like, wow, that'd be interesting to live there.
Yeah, and for people who don't live in California, a house that costs $24 million is not as outlandish as you might think. As a total aside, which we can cut out later, they put a house for sale recently near a place where we like to go tide pooling. They put it on the market for $108 million. So
wow. So what's the equivalent of that in the formal verification world?
Probably maybe Z3 or something like that. Something.
Okay, all right. Well, you're gonna tell me what that is. So you tell me, Mike, when I say to you formal verification, what does that mean? Maybe our listeners, they may not have ever heard of these tools. Maybe they've heard of them. They don't know, they can't imagine. And I think I feel this way too. It's like, what is it? It's not a program, or it is a program. You don't just run it. You can't deploy it, right? What is formal verification? How would you answer that one?
Yeah, it's a good question. So 2 things about it. One is that I think, broadly speaking, it's just anything that verifies that a program or an algorithm does in fact implement the thing that some specification asks for.
Mm-hmm.
There's sort of implied in this process that there's some sort of specification that you are trying to verify. And like I read somewhere recently, I can't remember who it was, but they were saying that they get kind of annoyed when people say that they have written code that is proved correct, because that's kind of that's kind of an overstatement. So what you're proving is that it matches the specification that you've provided. So, it's still entirely possible that the algorithm does something silly or
Like
uh,
my first example of draining the bank account.
yeah, I mean and there's that, that famous quote by Knuth where he says, you should test this algorithm by yourself. I've proven it to be correct, but I haven't actually run it. So something like that. But
Well, wait. So your first definition here is you've got a spec and you're maybe demonstrating it's correct, but formal, the word formal sounds like there's something else going on here, because what you first said, my immediate thought was, wait a minute, I've got unit tests. That's demonstrating my program is correct. I may also have property-based tests, which can run through a lot of arbitrary scenarios that are spontaneously dreamed up by a property checker. That's not quite the same, right?
yeah, I think the key difference is that within the context of the specification, what you're hoping to get here is something where it either says yes for every conceivable input, this is going to do what you specified. A lot of times what you're looking for is here's a counterexample that where your algorithm doesn't work.
Hmm.
So the difference between this and just testing is the sort of exhaustiveness of it, the fact that it is either trying every conceivable possible state, or it's in certain other cases, certain other tools, it's doing a sort of mathematical proof that the thing that you are proposing is actually happening.
That sounds pretty cool. And then at the end, it just stamps like a QED on your program. Like that Simpsons episode where they stamp sane on his hand and they let him out of the insane asylum.
It's exactly like that. Yeah, there's a Simpsons
QED.
analogy for everything.
So I like your description there. Actually, that was a pretty, like, I felt like I really understood what you were saying. Maybe I didn't, but I feel that way. So I'm very positive about that. Do you know where the stuff comes from? Because I mean, they use these in math, right? I mean, is it different what they're doing when they're using proof checkers in mathematics? It sounds kind of similar.
Well, yes and no. I mean, I think so. The formal part of the formal methods does imply that there's some mathematics involved here, and I think fundamentally the mathematics is logic. There's a various techniques that people use for these formal verification methods, but I think they all boil down to some extent on mathematical logic.
What do you think? It's so, like, I hear about this stuff and I think, wow, formally proving programs. That's cool. Can I just feed my program in and it would feed, it would formally, it doesn't usually work like that, right? You have to write something, you have to interact with some tool.
Yeah, there's usually a tool, and at the very minimum, there's some sort of language that you have to put the specification of the algorithm in.
Which could be a
Um,
DSL or like a full-fledged programming language.
yeah, there's things like we'll talk about some of these later, but there's things like you've been talking about TLA plus a bit, and that is sort of a language unto itself.
Hmm.
But there's also things like Lean, for instance, is a proof assistant language, but it's also a functional programming language if you choose to use it that way.
I have never looked at Lean. Is Lean the one that they used for proving mathematics?
Yeah, they're using Lean. Lean comes out of Microsoft, I think, and they're using it quite a bit to, they're building entire curricula on trying to prove basic mathematical things. And we talked a bit a while back about the guy who's trying to use Lean to redo the proof of Fermat's last theorem.
Oh yeah, that's right. We did like a news in the news thing, and that's where that first came up for
Yeah.
me. Yeah. Okay. All right. So, how long have these things been around? Do you think? I actually don't know the answer to this. Do you know off the top of your head? I don't know.
Yeah, it's a tough question. It kind of depends on, what you consider to be an actual verification tool. I mean, the roots of it go back to probably at least lambda calculus, and there was the stuff that Tony Hoare did in I think the 1960s and 70s, when now it's called Hoare logic, and there's a tool that came out of that called CSP, which dates back to late 70s, early 80s.
Okay.
Um,
All right. So these tools are not. I mean, they haven't been around a long time.
The first time I ever became aware of this stuff is actually with respect to hardware design. I don't exactly remember where it was, but I remember very early in my career hearing people talk about things like Verilog and VHDL, which were these languages that were specifically designed for for designing silicon, designing chips
Mm-hmm. Mm-hmm.
because they're so hard when the density of the circuits gets so high, it's very hard to make sure that they're still going to work correctly, and so they kind of developed these techniques to design in correctness before they started actually etching things onto silicon.
I remember talking to a chip designer once at a very large company, and he had described something similar. And he said, "Yeah, we have to like make sure that we're not bleeding too much and that we're not drawing too much power. And this is the system on chip thing. So like I've got a camera portion of the chip, and I've got something that manages battery, and I don't know. I've got different chunks of the chip that have different responsibilities, right? Something that manages a microphone." And they would, as the chips got smaller and smaller and smaller, they had the tiniest wires and the tiniest filaments of wires that are in the circuit itself, and they had to like run it through a proof system to make sure that it would actually function, in addition to all these other tests. And I said to him at the time, like, wow, that sounds like a sat solver or like SMT or something like that. Is that in the same category? Because maybe I'm drawing a bad distinction. In my head, you've got formal verification, which implies logic and proof. And on the other side, and it's not to denigrate that stuff, you've got things like unit tests and property-based tests and maybe fuzz testing. Like we're going to run a bunch of examples through and see how it does, but we're not exhaustively checking. Is that a fair distinction, I guess? I mean, here's a different question. What about like static analysis tools or undefined behavior detection tools?
Yeah, that's a good question. I'm not sure how you'd classify static analysis tools. I do think that probably both of those things would fall into the sort of larger umbrella of formal methods.
Hmm.
Sometimes people even include certain programming languages into the formal methods umbrella just because they have features that are designed to help you write more correct programs. So some people will consider things like Haskell and OCaml to be part of the toolkit of formal methods.
Camel surprises me there. Okay, so wait. Maybe we should just talk about like the what, like, can we bucket these things? So there are these programming languages, and some people just say these are DSLs, and then there's like a tool that you run. So you write a spec, you write a specification, and then you have some program like a dedicated platform or tool that runs, and it evaluates the spec, but it's not like it's going to go and read your code in most cases, right? I mean, what are the categories of these? Is there a way to like bucket them so I can at least keep them straight in my head?
Um, Unfortunately, I think there's a lot of different ways to bucket them, but one way that I have been sort of categorizing them is, and even this is a little bit of a leaky abstraction, but there seem to be sort of three broad types of tools. One is what people call model checkers.
Okay, so TLA plus is a model checker.
Yeah, TLA plus. There's a tool called Alloy. Quite a few of these. Most of them are pretty well known.
Hmm.
Well, I guess there's TLA plus, there's Prism, there's Fizbee, there's P. I think also out of Microsoft.
I've heard of
Um,
PE. I haven't heard of the other ones. I've heard of TLA plus, of course.
yeah, and TLA plus is the one I'm. Alloy and TLA plus are the ones I'm most familiar with. These also are based on logic, so I think the original model checking work was based on what people call temporal logic,
Hmm.
and temporal logic is actually part of the name of TLA plus.
Yeah, temporal
Um,
logic of actions. Yeah, the book "A Science of Concurrent Programs" is really interesting for the history of this. I'll give you a chunk of it in a second here, but we're still like trying to. I'm still trying to like just keep the thing straight in my head. When I hear about a new one, I want to be able to put it in a category of okay, that fits in this category X. So you mentioned model checkers, and you said there are other categories.
yeah, so model checking is one, and then there's another kind of broad category of what people call proof assistants. So
That sounds like model check. That's different from model checkers. You think?
Yeah, it's a little bit different from model checking, probably a little bit more directly mathematical because these tools are really literally trying to do mathematical proofs.
So
So
you're trying to actually build a proof. You're not just saying, here's a spec, prove that it is correct. You're saying, help me construct a proof.
yeah. So there's there's a variety of tools in this category. There's Lean is one of them. There's Agda and Idris. The unfortunately named Coq,
Calculus of constructions.
COQ, which came out of France. Um,
I thought they were going to change the name of that thing finally. There was controversy
yeah,
about that for a long time.
they're supposedly renaming it to the Rock Solver or something like that.
Mm,
Um,
mm.
but yeah, so these tools, they usually there's usually like a language part, which allows you to build the specification and build, the proof. There tends to be both a language and a tool with a lot of these.
Or
The
even like
proof
a
is
language and a compiler. Like,
well, there's the proof assistant part is reflective of the fact that you can kind of build these proofs, stepwise. So
mhm.
there's not necessarily an expectation that you are writing the entire proof you can do it, but
Oh, okay.
there's
Okay.
there's not an expectation that you write out the entire proof immediately. So you can sometimes use these tools to help you sort of construct the proof piece
Okay.
by
You know
piece.
what? You are helping me here actually, because you said model checkers, and I think, oh, okay, like TLA plus. I have like an example in my head, and you said proof assistance. I was like, wait a minute, what? How's that different? Yeah, what you're saying makes sense. You can use these to construct proofs. They help you construct proofs. You could construct them stepwise. I like that. That's a good distinction you made. For me, it's
Yeah,
helpful.
and it's not an easy process, and it does require some, a little bit of mathematical thinking. We've probably won't go into this in detail on this podcast, but there's this famous paper called Propositions as Types, which we probably will talk about in detail some other day. But Propositions as Types talks about what's now called the Curry-Howard isomorphism,
Yeah, or
which
the correspondence. Yeah, I've heard of that. Yeah.
so there's this sort of idea that you can think of types as being logical propositions or functions from one type to another as being a logical proposition. And you can think of executing programs as being, proving things.
Hmm.
It's a hard idea to grasp. I still have not really grasped it, but there is this idea that you are essentially doing a proof as a program.
If you're
Uh,
writing a type.
yeah, I mean, there's a little bit more to it than that, but yeah.
So wait, go ahead. I'm sorry. Go ahead.
I was just going to get into the third broad category of
I just
thing.
wanted to say, like, you go from model checkers to proof assistance. Model checkers sound a little bit more pedestrian than proof assistance. Like, if I want to know that my program is correct, I feel like, oh, I go to this model checker thing, I write a spec of my program, the model checker checks it, and maybe that's proving it. But now I've also got a proof assist. That sounds like more heady, and it sounds like more like I probably need a PhD in mathematics to go. Am I thinking wrong? Like, are those reachable for me too?
I think that model checkers are a little bit more popular in terms of what people are actually using than proof assistants for
Mm,
that very reason.
hmm.
One is that it's not that they're simple. I just think that if you are a programmer, it's easier to understand what a model checker is doing than it is to understand what a proof assistant is doing. I don't know that that's true of everyone, but that seems to be true for me. I've played
Yeah,
with
me
the
too. Yeah.
tools. I played with the Alloy and TLA Plus tools, and I kind of get what they're doing.
Hmm.
You set up this specification, then you run something, and it runs. It shows you statistics about the things that it's running through.
Right. There's like a state space, and there's moments in time. Although time's the wrong way to think about it. There's successive states: state one, state two, state three.
Yeah, which is certainly not to say that it's easy, but I think as a if you're coming to it from the standpoint of being a computer programmer, I think it makes a little bit more sense. It just seems like
Okay.
sort of a more sophisticated version of testing,
Yeah, it
whereas
does kind of.
I think proof assistants are a little bit. You do have to have a little bit more mathematical and logical grounding to get what's going on there.
Yeah, not my background. But so you had three categories. There's a third category?
Yeah. So the third category, which is a little bit contrived maybe, is category of things that use either SAT solvers or what they call SMT solvers.
Oh,
Um,
I thought those were kind of what you could called proof assist. Those are different from proof assistants?
yeah, a little bit as I understand it. So probably the best known one is yet another thing out of Microsoft called Z3. And I am reluctant to go into these in great detail because have a very limited understanding of SMT.
Oh.
But as I understand it, SMT is kind of an extension of SAT solvers. So SAT solving is this sort of famously NP complete problem that you can sort of take every NP complete problem and reduce it to a SAT problem, and
Mm-hmm.
it's really about satisfiability. You have this formula, and can you find inputs to that will actually satisfy that formula? And as I
Mm-hmm.
understand it, SMT is kind of an extension of that, where instead of having just logical formulas, you can sort of extend it to expressions and things. So
Oh, okay.
uh,
So
but
it's kind of like if I have three people and we're all trying to figure out, we're trying to agree on a place to go to lunch that will satisfy all three of us. That's three sat. That is an NP complete problem. And you can use these tools to do what? What would you do? How do they find it where we're going to eat lunch?
yeah, I don't have a good sense of how the tools here work, but I do think it's kind of a slightly different approach than both model checkers and proof assistants. Although
Uh,
I think the reason why these are hard to categorize is I think there are model checkers that are using SAT and SMT approaches and
oh.
so forth. So it's probably not a clean separation.
I want to read from A Science of Concurrent Programs, Leslie Lamport's book. This is about the origins of TLA Plus. TLA Plus is a model checker that gets used to verify distributed systems algorithms. So here's what Lamport writes. Programming is not just coding, it requires thinking before we code. Writing algorithms taught me that there are two things we need to decide before writing and debugging the code: what the program should do and how the program should do it. Most programmers think that the code itself adequately describes, quote, how the program should do it. But I learned that we need a higher level, more abstract description of what the program does. Sidebar here, what he's saying. It sounds to me like the code is self documenting. And you know what? Guilty. I have said that. Anyway, one more paragraph here from Leslie Lamport. Lamport continues. Engineers who build complex systems usually recognize the need for describing what their programs do in a simpler, more abstract way than with code. I decided that abstract programs written in math provided such a way for describing the aspects of a system that involve concurrency. By about 1995, I had designed a complete language called TLA Plus that engineers could use to write abstract programs in TLA. This is the temporal logic of actions, comes out of this temporal logic from the late 70s. He talks about this in the book. And he's got this language that he calls TLA Plus that you can use to write abstract programs. And he talks about abstract programs are programs that they describe abstract behaviors or behaviors in the abstract. They're not programs you just deploy. Like I can't I can't just write this program to satisfy the ticket. I write this program to describe my program that satisfies the ticket. What do you think? Is this plan going to take off? Are we going to make millions of dollars on this?
um, yeah, so I think this is kind of where the challenge lies. Is people like us want to write programs that work, but
Yeah,
we're
yeah.
not super excited about the idea of writing a program before we start writing our program. And um,
Was
I
that
think,
right one to throw it away?
yeah, I am becoming a little bit more sympathetic to that idea for a couple of reasons. There's one tool called Daphne. It's a language, but so you can write formally proved things in the language Daphne, and then it generates other languages.
Hmm.
So I think that idea has some promise where maybe you write something as a formal specification, formal proof of your idea, and then it magically generates real code in a conventional language for you.
Yeah, that sounds cool. I don't want to
Um,
duplicate my effort. Daphne, by the way, spelled Dafny. We'll include a link to that one. It's if you never heard of it.
yeah, and I think I've seen quite a bit of work recently also about using, not surprisingly, LLMs to sort of
Mm.
automate this process.
That's
And
what we started with, right? Like it is automated reasoning almost, right? Or no, is it different?
yeah, I think Amazon actually tries to call out the difference between the two things,
Hmm.
but I think there is kind of a cross pollination between the two things for a couple of reasons. One is because this historical problem that people don't want to write programs before they write their programs. It looks like labor that doesn't have a clear return on investment for some problems.
Mm.
For certain problems, it's probably essential because getting them wrong is so potentially costly.
Hmm.
For just run of the mill programs, it's probably hard to justify the extra effort.
Yeah, that's why things like
But
Daphne sound interesting, or Idris. Idris also a programming language that you can write sort of proofs in using its type system.
yeah, and I've seen work where people are trying to use LLMs for a couple of ways. One is to sort of simplify the process of building the original specifications and proofs, and then the other thing that, as I understand it, one of the difficult things also about a lot of these formal methods is that you can go through all the effort to prove something is correct, and then you reach a point where you need to change the specification, so you need to change how the thing actually works,
Mm.
and you find yourself kind of back at square one is in terms of the formal verification. And so I've read some papers about people trying to make the transition from a change in the specification to a change in the proof a little bit more automated. Uh,
Mm.
Talia Ringer, who I was kind of following for a long time on social media, who's at the University of Illinois, I believe, has been working on that.
I have a kind of analogous thing that pops into my head, which is there is a specification or a description of a program that is widely deployed in industry, maybe because it's so easy to write and it is a kind of documentation, but like Open API or Swagger specs, it's really common to see and interact with these. Why did that take off? Maybe because it doesn't require rigorous mathematical, maybe it doesn't require logic, intuitionist logic or set theory or things like that. Maybe it took off because you can use it. I don't know. Does that a dumb analogy? Maybe it doesn't compare.
Well, I think there's sort of 2 points in there. One is I think OpenAPI is a little bit simpler in terms of what we're talking about with respect to specification.
Certainly not formal.
Simply laying out the parameters and the types to an API call is useful, but it doesn't say anything really about function and what
Okay,
correctness
that's fair.
looks like.
It's closer to documentation that you can run than it is to actually writing a spec.
Yeah, and I think another reason why that has gotten popular and this relates back to formal verification. I think is with Open API, there's a lot of tools that will sort of help you do it, and you end up with
Oh.
this thing where, like I worked in a lot of contexts where people almost demand the Swagger stuff so that they can test the API. I think that's one of the problems with formal methods is that there is no sort of simple entry into it. There's not like a thing that you can use that where you just have to annotate a function or something where you can use it in part but not in whole. And so
I had like a light bulb when you were speaking too. Another problem with it is that there's no user for the formal verification. Like you said, I had people demanding a Swagger or Open API spec because maybe they're working on like you're building a back end, they're working on a front end. They don't want to like come to you every time they need to know what the back end returns. They don't want to send millions of requests. They want to get the Swagger or Swagger UI so they could go into their browser and be like, "What is this return?" Okay, cool. They're a user of that tool. And maybe these
yeah,
formal verification tools, there's no user. It's like I'm writing my program. I am a user of this tool so that I can validate to me that my program is correct. I can't ship this verification off to somebody else and say, here, use this thing.
Yeah, I think there's a bit of a eat your vegetables aspect to formal verification where
I was just using Open API because I was like, see, developers aren't that lazy. They are writing some kind of spec, right? But I think you've sort of shown me that that's not a great analogy. I want to give you another interesting example, which is Microsoft's P language. Here's from their, I think it's from the GitHub description of P. This to me sounds cool. Okay, what I'm going to tell you, what I'm going to read from their thing. This is their writing. To address the challenges of asynchronous computation, we have developed P, a programming language for modeling and specifying protocols in asynchronous event-driven applications. This is a collaborative effort. It's in academics and Microsoft researchers. They write, unlike TLA Plus and Spin, a P program can also be compiled into executable C code. Aha, that sounds kind of cool. And then they continue. The programming model in P is based on concurrently executing state machines communicating via events, with each event accompanied by a typed payload value. A memory management system based on linear typing, and unique pointers provide safe memory management and data race free concurrent execution. In this respect, P is similar to modern systems programming languages such as Rust. So, a couple details there. One, you can actually write a spec in P, but you can compile that spec into runnable C code. And I know what you're thinking. The second paragraph says, you're thinking, C. And they're like, no, no, no. We'll use linear types to make sure that if you assign something to memory, you're only going to use it once. Linear typing is, it enforces the single use of those variables, and so you don't have data. You have memory. It's safe memory management. Now, this sounds kind of cool. What do you think about this, Mike?
yeah, I like that idea. Again, that's kind of the approach that Daphne is taking. It seems like more and more often the place where I'm hearing about formal methods and formal verification is in these distributed systems.
Mm-hmm, mm-hmm. Why do you think
Because
that is? Me too, but I just thought it was because that's what I'm paying attention to.
um, well, I think you see these methods in places where either it's really hard to get stuff right or it's really crucial to get stuff right, or both. So the place where I see them the most is so distributed systems, because it's so hard to get distributed systems right. It's worth investing the effort into, something which is not necessarily directly building the application.
Mm-hmm, mm-hmm.
The other place where you see this is in things like cryptography, where you want to make sure that that algorithm is correct, because the consequences of it being, having some sort of flaw are significant. Similarly with things like aircraft control systems.
Yeah, medical
You don't want to
devices, huge
medical
masses of
devices,
money.
right? So in those cases where people are willing to invest extra effort, that seems to be where formal methods are coming up. But
I mean, I think even
the,
more, you got the specter of Lamport saying, you are unlikely to write this correctly, at least the first
yeah,
time. So you should just sit down and think about what it should do, and then you should write down what it should do, and then you should write the application.
yeah, and it seems like now, so a lot of the work that you're seeing in this area is coming out of companies like Amazon and Google.
Huge
Um,
companies.
yeah, big companies where this investment is clearly both worth it and within their means.
Because we got to, like, small startups aren't going to pause for a week to write a spec of their thing before they actually write their product, which may or may not succeed in the market.
Well, yeah, I mean, I think it depends on what they're doing. So, that like there's this company Galois that we talk about from time to time, and almost all the work that they do is with respect to formal verification, but a lot of it has to do with cryptography and other sort of DARPA like things where the funding is coming from the government and the objective is to make sure that things are correct and secure.
Mm-hmm. You actually showed me an example from Cloudflare, which just published like just this week, maybe just yesterday or something. It was just we were planning to talk about this, and then Cloudflare is like, "Well, we do this too."
Yeah, they are apparently using it for DNS lookups or something.
Yeah, they called the system Topaz. They formally verify the correctness of their, this is from their article about it, internal DNS addressing behavior. To achieve this, we formally verify the programs written in a custom Lisp like programming language that our name server executes when it receives a DNS query. These programs determine which IP addresses to return. Whenever an engineer changes one of these programs, we run all programs through our custom model checker written in Racket plus Rosette to check for certain bugs before the programs are deployed. Oh, that sounds kind of interesting. So, but that sounds like another instance of, hey, we have this Lisp-like language. Racket is a Lisp, and we write the programs in that language. And then our model checker is pretty close to that, like pretty adjacent to that. It's not some completely separate DSL or some separate language that you have to go and put on your whatever hat and write that thing and then run the thing.
Yeah, I think it's also kind of I mean, this sounds dismissive, but I think it's kind of a small problem. And what I mean by that is that it's not a giant system that they're trying to verify. It's a fairly isolated and uh, well understood function.
Yeah, so maybe
Uh,
okay. I think what you're saying is like DNS is a problem domain where what you're trying to achieve is pretty well specified in advance. I guess is that an okay phrase for what you're trying to say?
yeah. So they're not trying to like formally verify an operating system or something. It's got a fairly clear scope and fairly clear objectives. I saw a similar thing out of Amazon where they have their own language called Cedar for specifying like permissions in the
Oh,
AWS environment,
hmm.
but they use Lean to formally verify that the Cedar specifications for granting permissions or denying permissions are actually doing what they think they're doing.
Jeez. It's pretty heady stuff. So I want to end by talking a little bit about types. We just sort of touched on this famous discussion, the Curry Howard correspondence, propositions as types. It's sometimes called by Philip Wadler. I don't want to try to get into that because there's a huge gap, chasm of interesting content in there that I am not prepared to jump into with you today. I came across this interesting passage in Lamport's A Science of Concurrent Programs, and I wanted to get your take on it. Lamport writes, this is about types, right? He writes, I believe types are wonderful in a coding language, and I wouldn't want to write code in an untyped language. However, I have found the kind of types provided by coding languages to be unsuitable for representing abstract programs. For example, type correctness for Euclid's algorithm means that the variables of x and y are positive integers. The simple type systems of most coding languages don't allow a type like positive integer. Moreover, those types are overly restrictive, disallowing some reasonable expressions. And now I'm going to sidebar here. This is me, Erik, talking. When I read this, I was like, wait a minute. This version of this book that I'm reading was published in 2024. Surely Lamport knows about dependent types. Comes from Martin Loef in the 70s. He must know about that, where you can create a type called non-negative integers or whatever. Anyway, so he's anticipating my doubt here in the next paragraph. He says there are type systems that allow the type positive integer and are not restrictive. They are needed to formalize the kind of math that mathematicians do, so their proofs can be checked by computer. However, those type systems are so complicated that I never tried to learn them. I didn't have to, because I realized that they are not needed for the math used to describe and reason about abstract programs. Instead, type correctness can be treated as a simple invariance property of programs. And just a note on that last sentence. I think what he's saying when he's talking about TLA plus is I could just write and assert that these integers are they're always positive integers, and then I can have my checker check the state space, right? Evaluate all possible states. And if my assertion fails, then my model checker fails. So I don't need those types. What do you think when you hear this from Lamport? He wants types. He's not into fancy type systems.
um, well, I probably have to take anything that Leslie Lamport says uh, as, you know, serious and probably more deeply, you know,
He's thought
he
about it
has,
more than we have.
he has a deeper understanding and a deeper experience with these things than I do. So I have to take it seriously. I do have like the idea of a dependent type seems to be so fundamental to the proof assistant world that it seems a little too dismissive, maybe.
I was
But
surprised. I was surprised by this.
yeah,
Yeah, because the calculus of constructions, and I'm very limited understanding of it. I've never tried to use it. I thought it was inspired by dependent types.
yeah, and there's a lot of work in that area in the propositions as type paper. He talks about how that dependent types is kind of a necessary addition to that world to make things work the way you want them to work.
Wait, hold that thought for a second. I just realized if you have never heard of dependent types and you're listening to us speaking here, we'll try to get into this in a future episode, I think. But the idea is if you think about a type system for programming language, you might try to write a function that takes a type, maybe the type is a string, and it turns it into another type. Maybe the type is integer, and maybe you could take a string and you can count the characters in it and turn it into an integer, right? So you're turning one type into another. And there is a connection to logic that we don't really want to get into here. But with dependent types, the idea is that you can take a value and produce a type. This is actually something that's really not common in programming languages we're generally using. But a language like Idris allows you to do this. So you can take a value like positive integer or whatever, and you can actually produce a type that your compiler can reason about. Non-negative integer is the type. And that's why they're dependent. So the type is dependent on the value. And so Leslie Lamport's example of types to represent positive integers, in dependent typing systems, you can do exactly that. You can write a correct division because you can make sure that you're never dividing by zero. Anyway, sorry for the detour. How'd I do there on dependent types, Mike? I just didn't want to lose anybody. We keep talking about dependent types.
Yeah, it's a tricky thing to understand. I think there's a really good book called The Little Typer, which goes into this in significant detail and is
Doesn't it,
not
that's the
too.
Idris book, right? Too, isn't it?
It kind of has its own language, sort of. But
Okay. Okay. I'm
um,
wrong then.
the other thing I was going to say, which is true sort of across formal methods, is that a lot of these techniques, including TLA plus, sort of punt when it comes to floating point numbers.
Hmm.
there's a there's difficulty when you get into the real numbers specifically because they have to be, you treat them as floating point numbers typically on computers, and floating point numbers have uh, issues with things like order, and so it
And they're
just
uncountably infinite too. Is that why? Is that a problem?
uh, yes and no. So like there are some of these tools can handle situations where there's an infinite set of things. But yeah, anyway, just as a general aside, a lot of these formal methods don't work well with, if you wanted to formally prove like your linear equation solver, that's
Mhm.
kind of something that's beyond most of their capabilities. So still so far.
I guess I want to give one last shout out here to the dependent types. So you pointed me to Hillel Wayne's hilarious post, Let's Prove Left Pad. And he has a GitHub repo called Let's Prove Left Pad. And there's, I don't know, like 3 dozen different proof assistants and model checkers and programming languages that he's formally proving left pad in. My favorite one was the Idris example. And in the README of that one, he writes, in a dependently typed language, theorems are just a certain way of looking at types, and proofs of theorems are just programs with those types. That means that we can prove a program is correct just by giving it a precise enough type. Now, that sounds pretty cool. If I can actually construct a type that the compiler will actually compile, the compilation of that type, that it's a valid type, is itself a proof. I've proved something. And actually running the program is simply evaluating the proof or reducing it. That sounds kind of cool. But maybe I'm never going to use this in my day-to-day programming. What do you think?
Yeah, I like the idea a lot. Same situation so far where if I'm writing a program to add up a bunch of numbers in the column of a data frame or something like that, I don't imagine I'm probably going to whip out my proof assistant to verify that I'm doing it right.
Yeah. I mean, I think time too is really hard here, right? Famously, there's safety properties and liveness properties in distributed systems. Liveness properties are often like eventually something will happen. And this is what TLA Plus was written to express. Eventually, a thing will happen. And that seems pretty hard to write as a type.
Yeah, I don't know how that works with, because I think you are sort of have to incorporate temporal logic into those systems.
Mm-hmm.
And I know nothing about temporal logic and types. So,
All right. Well, I think we're just about out of time here. I was really hoping we'd get to the question to resolve the question of, am I ever going to use this at work? And I don't think we answered that question.
I think the answer for me is, unfortunately, probably not, mostly because I'm running out of years to work. But
You don't want to work anymore.
it's, I do believe, so I have this, I've said this before on other episodes, I do have this kind of naive and unsupported belief that these methods will become more common because people will invent tools that use LLMs or other technologies just to make them simpler.
Hmm.
I don't have any really direct evidence of that yet, but it does seem like people are working on that sort of thing, and that some of the issues around writing code that is not the actual production code and maintaining that code and trying to keep it in line with the implementation will start to go away as the tools around LLMs get better.
All right. I'm going to leave you with the last word there. I have a little bit of doubt about what you're saying, but I'm not even going to express it. Last word there, Mike. Thanks so much for talking to me this week about formal verification. I honestly think in the future we should try to go do propositions as types. It'll get real metaphysical and
Yeah,
mystical.
I'd like to cover a lot of these topics in a little bit more detail. I think what we were trying to do here really is just to make people aware of the scope of what you can do in this field rather than trying to explain any of them in detail, because, partially because we don't understand any of them in detail.
I have trouble keeping this stuff straight. I hear about a new thing and I'm like, okay, what is that? And your description of model checkers, formal proof assistants, sat solvers. Okay, I think that helps me. I think that helps me bucket them a little bit. Some of them are also programming languages, but others are just specs, DSLs. You know what I want you to do? I want you to listen to Third Coast Percussion. Listen to the Currents Volume 3.
I already did that at the beginning of the podcast, remember?
Oh yeah, we'll listen to it again. Okay, I'll see you later, Mike. This has been Picture Me Coding with Erik Gaker and Mike Mull. Thanks for joining us this week. We'll see you again next week.
See you next time.
Bye bye.